So you
Good morning, everybody.
where you can see
Can I have two people to come up? Volunteers. All right. What's your name?
Dan.
Dan, nice to meet you.
Pigeon.
Ben, nice to meet you again. All right, Dan, I'll get you to write a message inside of this envelope. How you doing today, Ben? Good. Thank you. Now I can't see the message, right? I'm gonna say it's going from
Dan.
Dan to Ben. Now, if you were to send this message to me, the server,
Yes.
I don't see the message right away, and in transit, it was hidden, right? No one can see what's in here. But if I were to maybe look at all this information on the outside, like who it's going to, who it's from, where it's from, and the exact date and time it's from, and then save that. Or maybe I want to take a look inside and make sure that I agree with the message. Or perhaps I want to give the message to my friend over here so she can read and learn from it as well. Now, can you guys tell me, is that message still private? No, it's not, right? Now I guess I'll finally give it to the recipient. I'll read it.
I got some mail. Good morning.
Thank you, guys. Before we jump in, a little about myself. My name is Leonardo. I just graduated high school and I'm fascinated with embedded software and cybersecurity. If you're anything like me, you're worried about how secure your message is, and more importantly, who might be viewing that message or using it. That concern is what made me start this project, right? It's my new passion project, Carrier Pigeon. I will mention the project is more of a proof of concept and a base for me to build on, to practice some fun ideas I had with radio. We'll start today by taking a look at some of the concerns I have with instant messaging providers, and then together we can come up with a way to alleviate these concerns. When it comes to the first and arguably most important, it's weak privacy protection. There are a surprising amount of current instant messaging providers that are not end-to-end encrypted, and some that just scan for your best interest or run-of-the-mill ad personalization. Secondly, data exposure is beyond just your messages. Privacy is not just your message contents. Now, what do I mean by that? Like I showed earlier in the example, metadata can be logged and can provide information such as location, date, time, who it's going to, where it's going to, and not just that, but that can be used to piece together social circles or patterns in your life, just what your everyday life is. There's also AI training going on messages on certain platforms and soft deleted data, which means maybe the message you deleted today won't be deleted till a day or two or a week later in the server backend. Finally, policy control and external influence. Now, some countries just don't even have encryption to start with. They have it turned off, or their governments have backdoors, or companies have backdoors. There are certain legislations that can be changed without your control, and policies, of course. All of what I just said is a threat to your privacy. In my humble opinion, private messages should stay private. So that brings us to the idea. What if we cut out the middleman? I set out to create my own decentralized communication device, where there is no server holding the data, no plain text is ever visible to anyone except for the sender and the recipient. To accomplish this, I decided on using the ESP32, equipped with a LoRa radio module. Now, if you aren't familiar, let me introduce you to the ESP32. ESP32 is a low-cost Wi-Fi controller, or microcontroller, that has Wi-Fi and Bluetooth capabilities. Now, firmware can be written for the ESP32 in a variety of languages, including code blocks, if you're not as advanced with syntax. Due to its simplicity, the sky's truly the limit on what you can do with it. It's very powerful and very cheap as well. You can usually pick one up for $5 to $10 online. Very much recommend for any project you're looking at. Now for LoRa. LoRa is a radio communication technique based on spread spectrum modulation. And there are other forms of it, like LoRa WAN, where it's more like a wide area network, but what I'm using is just point to point. Using lower frequencies, LoRa can effectively communicate through chirps at longer ranges than typical radio with lower or cheaper equipment, I guess. This range can be extended to, we'll see, but it can be extended with larger antenna, relays, or better equipment in general. The world record, just a side note, for the longest LoRa communication is 1,336 feet, or kilometers, I mean. Which is, feet wouldn't be that amazing, kilometers is much better. Just another note too, the frequency we are allowed to use for LoRa in North America is US 915, which is around about 902 to 928 megahertz. Now for the fun part, I'm going to let one of you guys try it. We need one volunteer.
I'll do it again.
Take this one.
Yep.
All right, so to power on, you press any key. I will, Now, I would like you to start pressing, obviously, the 12-character passphrase, you're going to want something with higher entropy, but for now, we'll just use an example passphrase of 12 H's. Just press H 12 times. All right, I have this little window so you can see me working with this as well. I'm going to press H a bunch. I had this great idea last night. I was like, what if I put a camera on the screen? All right, now here started the handshake. I will also press enter. Now this starts the ecliptic curve handshake, Diffie-Hellman, to derive the key. As you can see now, we are connecting. And you can go ahead and send me a message. Is it backwards?
Nope.
Perfect. I tried to invert it last night too. And there you see. ATLSECCON. Goes both ways. Obviously, I can send him one. Say, hey. And to power off, you simply press escape twice. Which puts it into light sleep mode and puts the e-paper on the idle screen. After I got the handshake working and encrypted messages finally sending between both devices, my first thought was, how far can this go? So I got to grab one of my friends and I got to testing, using the tiny antennas that came with the devices, which you saw are very, very small, and I think they cost around $1.50 online. I was able to reach a range of around 250 meters in open air and 120 meters in a more signal-dense area such as the mall. Using a larger 915 millihertz antenna I purchased online, this one right here, and a specialized LoRa antenna gifted to me by someone at DEF CON 902, shout out, I was able to extend that range quite a bit further. Range is around 500 meters through thickly wooded area on a rainy day, which messes with the signal, And a clearer day in the same spot, I was able to reach around 700 meters. Quite the improvement. Although these ranges are decent for the equipment I had, I wanted more. Now you may be wondering, how can we extend this range further without huge antennas or different LoRa modules, more throughput, or higher transit power? Obviously, nodes are a valid option, and many other LoRa devices use them, but I didn't want to just go the classic node route. I had a far more interesting idea, in my opinion. That brings us to the theory I've wanted to test since the start of the project, drone-based radio propagation. Hence the name carrier pigeon. Now, I've connected this little diagram to explain the main idea. So essentially, my theory was, since LoRa works best with direct line of sight, if I could attach a simple relay to the bottom of a drone, it would act as like a very, very low atmosphere satellite, essentially. The idea is, right, say there's a tree, I should have drawn a tree in there. Say there's a tree in the middle of the two devices, right? It's no longer direct line of sight, and very often, if you're in a longer distance, you will run into a wall or a block in your path. So looking straight up in the sky, you can obviously see the drone, and it's usually not blocked unless you're indoors, and even then, it's one wall, right, as opposed to many. So ultimately, the theory was, should extend the range quite a bit. So I quickly put together a little dumb relay that would essentially resend packets if received from either of the two devices. And it would check the hardware IDs to make sure it was part of my devices. I 3D printed a case for it and strapped it to the drone. Using a tiny antenna at a height of only 120 meters, I was able to quadruple my effective range. Yes, quadruple. And keep in mind, this is with the $2 antenna on the drone. I was able to reach an effective range of roughly 3 to 4 kilometers with next to no packet loss, which is pretty decent, considering. It was only 120 meters. The drone, not legally, can fly up to 500 meters, and the antenna can obviously be upgraded as well. I find this very fascinating, and I want to continue my research in this and stretch it to its extremes, because I feel like with a bigger antenna, better positioning, and higher up legally, of course, I can get far more range. I'm thinking somewhere in the ballpark, 20-ish kilometers. Does anyone have any questions for me before we dive into how this all works and is secured? Yep.
Yeah, so I have a quick question. So obviously this only works if both ends are online at the same time to receive the signal you're sending out. Do you have any ideas on like something similar to, say, the Briar messaging app, where you have a permanently online station that caches the incoming messages that you sync to when you come online?
That could work, yeah. I could, it would definitely be a possibility, but you would have to do something with like rolling keys so it stays secure, obviously. The idea for this would be peer-to-peer. You kind of have a time and a code you would use. But it's definitely possible to do a station where you have like rolling codes that are maybe a handshake every 30 minutes or a handshake every 10 minutes, between your two base stations that are constantly online. But then also, the thing behind that as well is my idea with these would be, okay, maybe the settings somewhere you don't want to be found, right? Say it's like a situation where you want to send a message and you don't necessarily want your location to be found out. If you have constant rolling packets heading to a base, they can use the received signal strength to like trilaterate where you are with it. So my idea with this would be a little more anonymous, I guess. Yeah.
What spread factor and channel width are you using for these?
I use a spread factor of 7.
Okay.
I don't know the channel width off the top of my head, but I can check right after if you'd like.
Cool.
Yeah. All right. All right. Now I'll quickly get into this. Don't get intimidated. It's the hardware level is relatively simple. It's only a couple of modules. So we have a battery, obviously, ESP32, a M5 card keyboard, an e-paper display, and a LoRa module. As far as the firmware, it's broken up into 3 main layers. This is for separation of concerns, so that later on, if I did want to like you said, build it off into a separate project with the same base. I can easily change things without it breaking. It's all split off. So the domain layer is mostly low-level functions for modules. So we have like a LoRa function or a LoRa module, input for the keyboard, and so on. And then service layer, you can imagine that's like the glue of the project, right? It holds together the domain and the application layer. This is stuff like packet parsing, protocol layer, message buffers, you know, displaying messages through the library at the end for the display. And then the state machine is the application layer. This is where everything is tied together. A little more about the hardware. So I use an M5 card KB, which is the smallest keyboard I could find. I thought about reverse engineering a Raspberry Pi, but not a Raspberry Pi, a BlackBerry, I mean. But I couldn't find a BlackBerry in time, let alone two of them. Kind of extinct, believe it or not. So I found this roughly $10 online. And then I use an SX1262 LoRa module, roughly like $6-ish online. And then I use a 3.7-inch wave shared e-paper display, which is roughly $10 as well. Bring the build cost to right around $30, including the ESP32. Each of these components has their own corresponding firmware module, which I told you about earlier, in the domain layer, that keeps everything clean and simplified. It's like, these are all based on pinouts for the most part, so you have to control like the pins with functions, which is, it took a while to get used to at the beginning, but it's good to keep it separated into multiple files rather than building one clunky mess. And you may have noticed I did not mention batteries in the component list. Now, I'm not cheap per se. When the opportunity arises for some free lithium-ion batteries, I am going to take it, you know? That opportunity arose one night after work, and I found 20 disposable vapes sitting in the parking lot, literally. Each one of these had a lithium-ion battery inside. I tore them all apart and I extracted a couple that were healthy and surprisingly almost perfectly matched the required specs for the ESP32. See there, some of the vapes and the batteries I was testing. That's what's in there. I'd like to thank my buddy Nate for this amazing idea. Okay, so majority of the project's crypto is done using a tiny C library called Monocipher. I didn't want to roll my own because I am by no means a crypto expert. It's a feature-packed lightweight library created by an amazing French developer. I am not going to try and say his name. I'm not French, unfortunately, yet, but he's great. I actually sent him an email and told him how much I loved his project. I'll quickly cover the specifics of what I used within this. For deriving public keys and private keys, or for generating private and public keys, and deriving the shared secret, I use Ecliptic Curve Diffie-Hellman with Curve 25519. And for Mac-based authentication, I use Blake 2B, and I use that as well for the key derivation at the end of the handshake. When it comes to message encryption, I use authenticated encryption with additional data with the Salsa 20 or Chow Chow 20 cipher and Poly 1305 one-time authenticator, which is pretty cryptographically secure in today's standards. Now, speaking of the handshake, I made this little diagram to try and explain it a little easier because if you haven't dealt with Diffie-Hellman before, it can be a little hard to wrap your head around at the start. Was for me at least, but once you get it, you get it. So, right here you have two devices, right? They both have their own hardware IDs that are different. They're never gonna be the same. So, when you turn them on and you start the handshake with 12-character code, which is never shared over the air, it starts sending hellos back and forth with a session nonce, the ID of the device, as well as the public key. The lower ID, since they both take the hello in, I suppose. They both receive the hello. The lower ID device becomes the responder. Only the responder will send back an hello app, which contains its personal nonce and the peer's nonce. This kind of validates that we are talking to the right person. Now, when it does this, it also takes that public key and the nonce and derives a shared secret and a session key from that information, right? which is the 12-character code and all the other associated data we have, which was sent in the hello. And then when the hello ACK is also received, it will do the same thing on the initiator side, which is device 1 here. Once that's done, we move into the auth phase, where an auth packet is sent with a Blake2B MAC authentication tag, which is built on both IDs, both nonces, and role binding as well, with the session key, obviously. So they're bound to their roles. And then when that auth is received, a connection is established on the second device, the responder, and then it will send back an auth ACK, and if the tag matches again on that end, both devices are connected through a secure tunnel with a session key that was never explicitly stated over here, and a 12-character authentication passphrase you put in as well, which was never sent over here either. Now, each of these steps are retransmitted if more than 5 seconds has passed without a response. This is kind of my technique to mitigate packet loss. So if a packet is dropped or misinterpreted, then it will be resent if it doesn't receive a response. So when preparing for a packet to be sent, a data packet, you first have to do some security features, which would be incrementing the transmit counter, building a nonce with the counter and the sender role, and then encrypting that data with the nonce and the session key. This is a message nonce, completely separate from the nonce we had at the start. This is a message nonce, completely separate from the session nonce we had at the start. Then we build the payload with the counter, then the ciphertext, and then the auth tag, as well as the role at the very beginning of the payload, which is a 1-byte role. Now, this might be a little daunting looking at the code, but I do luckily have a diagram for you. I love these things. So, like I said, we have the 1 byte at the start for the role. This is used for role binding, along with making sure that you're talking to the right person. You don't want to receive your packet back and be like, hey, this is a new message. So you need to know who it's coming from. Then we have the counter. This is useful because, I hope you know, but it's replay attacks, right? If someone replays your message, it could look, or replays your friend's message, it could look like a valid message, but it was a retransmitted signal, and it would pass encryption and authentication, right? But if you have a counter like this, which increments after every reception and every transmission, you're in sync. And that means if someone retransmits your friend's old message, nothing would come through. Packet would get dropped. Then we have 1 to 103 bytes for ciphertext, and then 16 bytes at the end for our MAC auth tag. Now, I put a 128-byte max on my data packet. I personally find that to be what worked best for my project. It can be stretched a little further with LoRa, but the longer you go for a straight transmission, the more you're dealing with like packets messing up or just dropping entirely. So it's honestly just better to keep it at 128 bytes, in my humble opinion. When messages are received, the data packet is then disassembled similarly to how it was built. We compare the extracted counter with the session received counter, and if it is less or not what we're looking for, then we will detect the replay and drop the packet. Then as well, we have the role comparison, which compares it to your role, and if they match, that's a reflection, right? It's your packet being sent back at you. We don't want that either. Now, obviously, this is also alterable. I could do group chat type of messages as well later in the future, and instead of just checking if this was equal to my role, I would check whose role it is equal to and maybe change the color, right? This is where you would hook into that. Finally, we decrypt the ciphertext with our session key and auth tag. And if the message successfully decrypts, that means the auth tag is validated and authenticated, and the message is good. You can pass it all the way back up through the callback, through the service layer, and then up to the application layer for the end user. Now, it's also good security practice to wipe our secrets when we're done. So as soon as the handshake is finished, I wipe everything we're not going to use moving forward. As you can see, that's most of everything. The only thing that stays is the session key. That's all you need to encrypt. Like I said, the nonces prior were the session, they're no longer needed. Private, public, peer public key, shared secret, and the pre-shared key we typed in the beginning are all not needed after key derivation and should be wiped to reduce memory leaks and other form of memory attacks. Once we're done talking and you press the exit button to finish your session, I also reset the counters and cryptographically wipe the message buffer as well, because I wanted to make sure everything was sanitary and that wasn't persisting any message data. That would also be bad practice. Now, this is an extremely simplified explanation. If you want to take a look at it, all of my code is publicly available on the standalone branch of my GitHub. Now, what does that mean for us? Decentralized communication means not relying on one company or another, or whatever their policies may contain. LoRa also is not operated using cellular, Wi-Fi, or Bluetooth, so if any of those went down, LoRa would still work. This means you, the user, the owner of the device, are independently communicating, and even if your packet is caught, it will be fully encrypted, with no metadata to be logged, and nothing to be scanned. Now you guys might be wondering, hey Leo, where do we go from here? And I want to ask you guys the same thing. Does anyone have any ideas or improvements they would like to suggest for the project?
Weather balloon. Instead of a drone, use a weather balloon. So
That is a
I
good
think
idea.
A lot of ham radio operators will do that.
That is a really good idea, actually.
Yep.
I'll look into it. Yep.
I was thinking about hiding them in courthouses, other trees.
That is a good idea too. I was thinking about doing something similar. I was thinking about climbing a tree and sticking a LoRa like solar powered node up at the top of it. I think that would be kind of interesting as well, just for building the LoRa mesh-tastic community around here. Yep.
About some kind of like re-receive thing, confirm that they actually received the message.
What?
Some way of confirming that they received the message. So.
There isn't yet. I will get to. Yeah. So that is a really good idea, actually. Yeah. I do have that in a later slide as something I really want to add, because it's something I wish I had time to, but a guaranteed delivery system is a little difficult to cram, unfortunately. I'll take one more if there is. Yep.
Have you tried different styles of antennas, like other than using omnis, using patches or anything like that for improved range?
I want to, but there is no like radio stores that I know of nearby, so every time I want to try a new one, I have to wait like 2 or 3 weeks for my Galley Express. It's rough, man. Halifax is rough. All right. Those were all great ideas. Thank you. Here are a couple I came up with while I was working on the project. So, encrypted media. That was something I really wanted to try and get done, but I just didn't have enough time to. I do have some of the code written, but it's just not functional at the moment. That would be encrypted photo video, encrypted voice messages. Now, obviously, this leads nicely into my next idea, which is multi-packet messages, which would be packet reassembly. Because obviously, a video would not be able to send in 128 bytes. Longer messages would also be a part of this feature, or update, I guess, because if I'm doing packet reassembly, the first thing would be getting a longer message to come through, which would be, say, 500 bytes long. Paragraph, you know? And then, of course, alternate message delivery systems. Like you mentioned over there, a guaranteed message delivery system is something I definitely want to incorporate in the future. And that would be like message reception, like an ACK for when you receive data, but the problem with that would be, okay, well, what if you don't receive the ACK? Then do you resend the message? But then if you resend the message and they did receive the message, then you got 2 messages before it got ACKed, you know? So it's like you have to come up with a smart way to do guaranteed message delivery. And then third and finally, GPS drone-based message delivery to maximize range. Now, this is a little different than what I did. I just flew it up and used it as a relay. In the future, well, the original idea was to do GPS-based delivery, which would be, I have a microcontroller that's attached to a flight controller on the drone. and then a GPS attached to the ESP32, and the ESP32 acts as like a controller for, I guess, seeing where you are, where you want to go, and then passing that to the flight controller so it can get as close to your friend's node as possible before transmitting the message. That would be ideal, and that would maximize the range to its very, extent. That being said, Carrier Pigeon is just my take on decentralized communication. Not the best or most readily available, but this project provided me with the base to start testing some of my interesting, weird ideas with radio. However, some extremely well-together alternative forms of communication already exist and are used by many. For convenient and straightforward end-to-end encrypted messaging, Signal is amazing, however, still centralized. For decentralized, LoRa node-based messaging, Meshtastic is a great project, but lacks a little bit in convenience and infrastructure at the moment. Security is also a little more lax on there, unfortunately. For decentralized communication using the blockchain, Session is worth checking out. It's very interesting. Not entirely fast or convenient for everyday use, but still a super cool project to check out. In conclusion, technology like this is fascinating. However, obviously at its current state, Carrier Pigeon is not scalable for the masses, nor is most LoRa messaging, unfortunately, but that's up to everyone to build that infrastructure, right? If nodes are very cheap, if everyone put out a node, it would be way more built out than it is right now. If one person in this room, or if every person in this room bought one node and placed it somewhere, that would, build out a very wide network as opposed to what we already have, which is very small in Halifax, unfortunately. However, if I could create this with a limited budget in a matter of weeks, you can only imagine what could be done with a team of engineers in a year. I decided to show off this project of mine to, I guess, inspire like-minded individuals to start experimenting with new protocols, new devices, and new ideas. I strongly believe we need to look to the future on how we can incorporate decentralization and other technologies in the messaging to promote communication independence for censorship, disasters, or just everyday privacy. Unfortunately, that brings us to the end. I'd like to thank you all for coming to my talk, and a special thanks to the whole Atlantic Security Conference Board for making this happen. If you'd like to reach out or stay in touch, come up and grab one of my business cards. And with that being said, does anyone have any questions?